So here's the first 50,000 years, and sure enough, gone along here, temperature goes up, carbon dioxide follows it by about 1,000 years. This is about a 1,000-year lag. So notice what I said. Temperature goes up, followed by carbon dioxide. I didn't say carbon dioxide goes up, followed by a temperature rise. So carbon dioxide looks like a result of temperature rise and not the cause of temperature rise. Let's see if this applies to the other rises. Our conclusion here is there's excellent correlation, but carbon dioxide lags by 1,000 years. So now we're going back between 100 and 150,000 years. Again, we see that here's a nice rise. What rises first? Not carbon dioxide. Temperature goes up first, and carbon dioxide lags again by about 1,000 years. Again, CO2 lags T by about 1,000 years, and there's this kind of interesting flattening. Remember that there's a peak here, and then there's a rather flat carbon dioxide. It doesn't fall. There's a lag in the fall of carbon dioxide even after temperature falls, and we're going to point that out later too. Here are two more rises. This interglacial actually came in two pieces, but again, both times carbon dioxide lags the temperature rise. And we do get some of this flattening thing too, so that flattening effect. So let's continue. This is not too, there's another lag here, it's not too pronounced, but finally if we go back to the earliest interglacial, they both rise at about the same time. Carbon dioxide does not lead except for this one single point. So we've seen many examples where carbon dioxide has lagged. In order to get anything that implies that carbon dioxide leads, we have to go back to the oldest data, which is also the least reliable, because it's the material at the bottom of the ice core, and that material has been squashed, and the guys that read these dates actually try to stretch it back out again. We're going to get to that point in a minute. So here we have CO2 rising simultaneously with ice core, and again we have this interesting flattening effect. So let's return now to this curve, which was the insolation, the correlation between insolation. We didn't like this because these 2 points, for instance, are not correlated. We said this can't be the reason, even though the correlation is good here. But if we now say that maybe the ice core guys stretched the data incorrectly, and that's called tuning the data. They tune it to known geological events, so that if you retuned the data, if you restretched it, you could get quite good correlation here. This peak would become this one. So I think more attention has to be paid to, there's possibly a problem with tuning of the ice core data. And if we tuned it differently, there would be good correlation with the insolation. And so maybe we were too quick to throw out this explanation of causation because of this disagreement. This agreement might be due to inaccuracy in the ice core data. That's what I'm suggesting. Well, let's sum up what we've learned so far, namely that insolation leads the temperature, which means that it can cause a temperature rise. Carbon dioxide lags the temperature, so it doesn't cause the temperature rise, it's a result of temperature rise. There was this interesting little thing we noted, that the CO2 seems to hold up, hold the up longer than the temperature does. And from these two findings, and we have to assume that the ice core data is not tuned correctly for times longer than 100,000 years. We conclude that the primary driver of climate is insolation, and that CO2 prolongs this peak temperature in some way. Well, going back to our graph that shows the correlation of temperature with insolation, let's see what the future, what is predicted for the future. Well, as I said, the insolation has already started dropping 5,000 years ago. It doesn't recover much here, About 60,000 years into the future will we get back up to insolations of the order of what we've experienced during the peaks, the interglacials. So we've got this big hole of lack of sun's radiation, or reduction, I should say, of the sun's radiation ahead of us. And so the insolation in the next 60,000 years is lower than it's been even in the past 4 ice ages. There's no spot here where there's as big an area above the blue line as until you go back perhaps 400,000 years. Here we've, as you can see, there's been many spikes which brought the temperature up. Now it turns out, of course, that each spike here, upward spike, does not cause a new warm period to start. It's only the exceptional ones that start interglacials, and we can't get into that because we don't have enough time. But let's look to the future. In order to do that, I pulled up this, brought up again this graph of the 5 interglacials that we've had in the past 500,000 years or so, and now we're going to compare them. We're going to superimpose this one on top of the previous one. First, let's look at an expansion of our present interglacial, and these are the 5 that we've had. Here is our present interglacial. It's about 10,000 years long. Its main characteristic is this little dip. As we look at the other, well, there's 2 main characteristics. One is it's extremely flat. Compared to the others that we're going to look at, it's extremely flat. And associated with that, possibly related to that, is the fact it has a dip on the way up. So this is the rise of our present interglacial, and it was interrupted for about 2,000 years. These tick marks are 2,000 years apart, back at 14,000 years, 14,000 to 12,000. There's an event called the Clovis event, which some people have associated with this. It's controversial, and we don't have time to discuss it. But if you want to look it up, it's on the internet.